Hello, welcome to this section, using the right plots to understand data. In the previous section we explored how to plot charts with images and maps. In this section we'll focus more on understanding what we want to say with the data we're presenting and how to say it effectively. We'll understand logarithmic plots and spectrograms. Then we will create stem plot, use colour maps and scatter plots along with histograms. And finally we'll plot the cross-correlation between two variables and learn the importance of autocorrelation. Now we move on to the first video of this section that deals with understanding logarithmic plots. In this video we'll generate two simple data sets, y exponential or logarithmic in nature and z linear in nature. We'll then create figures containing a grid of 4 subplots and 2 subplots containing the y dataset, one in logarithmic scale and one in linear scale. And finally we'll create another 2 subplots containing z dataset, again one logarithmic and one linear. More often than not, while reading daily newspapers and similar articles, one can find charts that are used by media organisations to misrepresent the facts. One usual example is called the linear scales to create so-called panic charts, where constantly growing value is followed for a long period of time, years, and starting values are smaller from the latest one by several magnitudes. These values, when visualised correctly, would produce linear or almost linear charts. This takes some panic out of the articles they illustrate. With the logarithmic scale, the ratio of consecutive values is constant. This is important when we are trying to read log plots. With linear, that is, arithmetic scales, the constant is the distance between the consecutive values. In other words, logarithmic plots have constant distance in orders of magnitude. We'll see this illustrated on the following plots. The code used to produce this figure is explained here. Depending on the data range, different log bases should be used. The standard base for the log is 10, but if the range of data is smaller, a base of 2 can prove to be more useful, as it will show more resolution within the smaller range. If we have the range of data suitable for display on logarithmic scales, we will note that the values previously being too close to judge any difference are now well apart. This allows us to read the chart much easier than if we represent the data in linear scale. The growth rate charts, where long-range time series data is collected, are where we want to see, not the absolute value measured at the time point, but the growth in time. We'll still get the absolute value information, but that information is of lower priority. Also, if the data distribution has positive, taking the logarithm of the value salary will help us fit the data into the model, as the logarithm transformation will give us more normal data distribution. We will exemplify this with an example code that shows the same 2 datasets, one linear and one logarithmic in nature, on 2 different plots in the same figure, using the different scales, that is linear and logarithmic. We'll be performing these steps with the help of our code. We'll first generate 2 simple datasets, y logarithmic in nature and z linear in nature. We then create figures containing a grid of 4 subplots. Next, we create 2 subplots containing the y dataset, one in logarithmic scale and one in linear scale. Create another 2 subplots containing the z dataset again, one logarithmic and the other linear. So, here's our code for understanding logarithmic plots. We first generate 2 simple datasets, y, which is logarithmic in nature, and z is linear in nature. We generate some sample data and 2 dependent variables, y and z. Variable y is expressed as exponential function of data x, and variable z is the simple linear function of x. This helps us illustrate different looks of linear and exponential charts. We then create a grid of 4 subplots, where the top row of subplots are data x and y, whereas the bottom row are of data z and z pairs. Looking from the left-hand side, column charts have logarithmic scales on the y-axis, while right-hand side columns are linear scale. We set this using the _y scale log for each axis separately. For every subplot we set a title and label, where label also describes the function plotted. With plot.grid, where b equals true, which equals both, axis equals both, we turn the grid on for both axis and both the major and minor ticks. Let's now run this code. So when we compile and run this, we obtain this figure. So you can observe how linear functions are straight lines on linear plots, while logarithmic functions are straight lines on logarithmic plots. Excellent! In this video we try to understand and explore logarithmic plots. In the next video we'll step ahead and learn how to create stem plots.